Assalamualaikum warahmatullahi wabarakatuh. Okay. So for the test one preparation, just an overview of the test one. It's going to be 1.5 hours. So you're going to start at 3 o'clock, and then we're going to finish at about 4:30, and then you must submit all the forms, all the questions, all the answers. You have to convert into PDF file and make sure that your file has all the pages. Okay, so, I don't want you want to be some of the pages missing from the file, from the PDF file. Okay, make sure that, and also make sure that you capture the whole question there. Right. And then you save the PDF, send through the Google Classroom. A question will be sent through Google Classroom, so you just log into your Google Classroom and download the question. All right. So there are two questions. There will be two questions. Question one will be on topic on semiconductor devices. Of course, there's a lot to cover, isn't it? So, but for the preparations, just read on the overview of power semiconductor devices. Okay, so you have to know what is the read the introduction here a bit. Okay, and then what is the losses, and okay, go to the power switching losses. What is the losses occurs in the for power switch loss. Read about some theory in there, and also some take a look on the switching losses. Okay, how to some there is a example on how to calculate the average, and before that you have to focus on this characteristic, the switching characteristic here. You have to understand what are those waveform, and what is this parameter that are involved here, isn't it? So basically, when you talk about the switch, there must be a pass, isn't it? So this is the pass to the switch here, isn't it? So you have a pass. Normally is a 0 to 10 volt. Depends. It depends. Some of 10 volts, some 15 volts. So it depends on the questions. Depends on the practical implementation. But normally we're going to be 0 to 10 volt. 0 is will be off state, and then 10 volt will be the on state. Right. But go further. Right. So this is the pass, which means the pass from driver circuit. You trigger the thyristor. For example, you trigger at this particular point. Okay, so in theory or ideal switch, as you start to switch on the thyristor, or the MOSFET, the IGBT, all the controllable switches here, it will certainly turn on, isn't it, instantaneously. But in practical, if you look closely, in practical, there is a delay time known as TD here, isn't it? This is delay time, TD. Even though you give the pulse or tell the switch to turn on at this particular point, but it wait for quite a few milliseconds here or microseconds here before it takes the device or the switch will start to turn on, isn't it? Look at this. So there is a delay time here, and then we start to see the current to rise, isn't it? So the current to rise until it reach its maximum current, then the voltage start to reduce. Okay, so there are rise time, so a fall of the voltage. This is TRY, the rise time of the current. TFV is the the falling time for voltage, isn't it? So we have voltage reduce because you want to turn on, isn't it? So reduce, and then you will complete cycles. I mean this is the turn on period. Okay, this is the turn on period, isn't it? Okay, and in practical, there is a small voltage here, isn't it? It's a small voltage conduction, we call it a conduction voltage here, and current start flow in the device. And then look at the turn off. At the turn off, we see that even though you give a pulse to turn off at this particular point, however, the switch only take in charge, I mean, it will effectively turn off only after the delay time here. There is a delay time at the turn off. Okay, so there can be a delay on the and sometimes it will be the same duration, but some of the some switch, they have a different delay time for on and off states. Okay, for example, here we have a shorter turn on delay, but we have a larger delay for the off time. So you start to turn off here, but it will only affect the switch after the delay time. Then we can see the voltage start to rise, isn't it? Because when it's off, the voltage across the switch will be equals to the whatever we have at the input. For example, in this here, when this is off, which is we have an open circuit here, isn't it? When this is off, the voltage here will be equals to VD, isn't it? Yeah, the voltage across open circuit will be equals to VD. So that's why we know that during this time we have the diode with the thyristor or the MOSFET or devices will be reverse bias. Okay, this is reverse bias, and this is forward bias. Sorry. This is forward bias, and this is reverse bias. Right? Okay. So in this off state also we have a this will be the off turn off duration. Okay, we have a TC off there. This is TC on, TC off, because there will be a different TC on and TC off, but sometimes probably you have a same TC and TC on and off, and that give you the losses. I mean the power, instant power here, and then you must integrate to get the voltage and current and the average power, and then finally you have this equation to calculate for your total switching losses. Okay, so focus on that. Look back at some examples on it. Okay, and try to understand the switching characteristic here, the generic switching characteristic. Okay, so depends on the questions. Some may have a different TC, different TD. Sometimes there is no delay time, isn't it? Can be no delay time. Okay, depends on the questions that will be given to you. All right, and again, look at how to calculate for the switching losses. That's it for the power semiconductor devices. And on the uncontrolled rectifier, look into the full wave and line source inductance. Okay, so you have effect of line source inductance. Be careful, right? So you have to understand why the voltages appear to be like that. For example, during this overlap, why this is 0 voltage here. So you have to be careful and look into the how to explain, how to sketch the waveform, right? So when you answer, please answer the complete, as much as you can, and try to be at the examiner's point of view. So you have to imagine if the examiner want to check your questions, to mark your questions, your answers. Of course, you have to explain, isn't it? You have to have a proper waveforms to show the overlap, for example. You have to have the circuit to show, if you want to explain, of course, you need to have the circuits here, isn't it? To explain anything in the circuits. So make sure that you look back on that. And of course, the some derivation, the equation involved. And we know that at the end, due to the source inductance, there will be some loss, isn't it? The voltage drop, voltage drop to the output side, and not only the voltage, but in some case we have the current also drop, isn't it? The IDC here because of that. So it depends on the questions, right? So look back on that. This is straightforward, inshallah. Okay, effect on line source inductance on current commutation, and look also on the back EMF here. Okay, some questions, some explanation on the back EMF, even though it's very small. The section small, probably you need to explain why you have this kind of waveforms. Going back. Okay, and finally on the control rectifier. Okay, look at the control rectifier. We start with the single phase half wave control rectifier, isn't it? And then we analyze the circuit, and then we identify this is a resistive load. But when it comes to resistive and inductive load, we know that somehow the thyristor here will be there is an extension because of R plus L, the thyristor or diode or thyristors or diodes. This is a control, isn't it? So it's the thyristor. So that thyristor will be extending its operations, even though it is already reverse bias, but due to the current still flowing in that direction, there is a extension angle, isn't it? Force the current to flow, even though you have a negative half voltage now. Okay, negative half supply voltage, but current still flowing in that clockwise, and therefore forcing the. So in order for you to calculate or to determine the beta here, you need to find the current equation, isn't it? So in this monograph, I've already explained to you how to calculate that beta, and this is simplified. You can actually refer to the while we're doing the uncontrolled rectifier. Okay, half wave uncontrolled rectifier, we do have derivation how to get that current equations, and this is the current equation. Okay, this is the current equation. So that will determine beta here. If you set, because if you look at the current equation here, if you set the current, if you know the current equation, and if you set the current at beta, the current will be equals to 0, isn't it? So in this case, you have, this is the current equation, even though this is for single phase, half wave, start with half wave. Then you can calculate, you can determine the beta here, because we know that at beta current equals to 0. So which means if theta equals to beta here, or if I may change that to beta, this is equals to 0, isn't it? According to the waveform just now, and therefore you have this equation here, all this equation there, sine, now it's beta, isn't it? Beta here minus v plus sine, forgot that, v big over z here, sine load angle minus alpha, and you have this equation here, omega L beta minus alpha, isn't it? E to the power of r over omega L. This is beta minus alpha. So make sure everything's in radian. Okay, everything should be in radian when you calculate using your calculator. Then you must remember there's one video on how to determine beta here, isn't it? I think the first video. So go back and look into the first video on how to use the calculator to calculate for beta here. Okay, so in this case, you can determine the beta there. And this is for a resistive inductive load, isn't it? For single phase half wave. When we apply the full wave rectifier, you still can use that question. What you call it? You still can use the equation. You can still use this equation here. Okay, you can still use the equation here to determine beta value here. All right. Okay, so if you come down and look into the single phase full wave rectifier. Okay, this is the full wave rectifier resistive plus load, isn't it? But we come to resistive and inductive load. It depends on the size of your firing angle. Okay, here, if you look closely, there are two conditions here, isn't it? So the size of L will determine the shape of the waveform. If you have a large L, which is a highly inductive load, this L here is very, very large. That means your beta is higher than the alpha plus pi. Or okay, there's one condition whereby alpha is greater than the load angle. Okay, alpha greater than the load angle. So if you have this case, you will see the output current will be in the continuous output current state or waveform. Okay, when you describe the operation of single phase R plus L inductive load, you always look into the output current. Okay, so the continuous output current, whereby if you look into the output current, it will become continuous, right? It will become continuous. So how to determine that? You look into this condition, alpha beyond than V. But if your alpha is below than the phi angle, okay, this is the condition. If you look closely, beta minus alpha here also can determine the phi angle. Okay, this is equals to the load impedance. But only for the case of low beta. There's a low L. If your L is very large, then sometimes you may not get the correct measurement. But however, the first thing you need to check whether it is a discontinuous output current or continuous output current is to look into the alpha conditions, whether it is below or greater than the load impedance. The load impedance or load angle. Sorry, load or impedance angle. Impedance or load angle. Okay, which is P equals to inverse tangent omega L over R, isn't it? So you need to find this, compare with alpha. Okay, so in this case, you can use, remember, we have the equation just now, current equation. Remember current equation just now? When we have a alpha equals to zeta, whereby when you analyze the half wave rectifier, this is the waveform that you analyze actually. You have a straight line there, then you have this, and that, isn't it? Sorry, it's now. We'll go back to the single phase half wave rectifier with R plus L. Okay, this is R plus L. This equation here. This is uncontrolled, isn't it? This is uncontrolled. You can follow the same derivation for you to get the single to get to this equation. This one. Okay, right. So this is for half wave rectifier. Okay, because that determine the beta here. So you can use the same equation here for the full wave rectifier. Okay, so in this full wave rectifier, and then right, in this case we know that this is when D1 and D2 operates, and this is D3 and D4 operation, isn't it? D1, D2, D3, D4. This is a D pula. T1, T1, T2, T3, T4, isn't it? So this is known as conduction angle. Yeah? How long it turn on here from there to there, from there to there. Okay, so this is known as a conduction angle. T1 conduct how long T1 and T2 conduct, and how long T3 and T4 conducts from that point to that point, and that point to that point here. So you need to identify, but first you need to calculate using the equation. The equation just now, still remember, we have that for half wave rectifier. Then remember, half wave rectifier. So you still can use that current equation for you just to determine the value of beta. Right? So let's look at the video is, let me show you. You go to my channel, my YouTube channel. Okay, go to my your videos. Okay, playlist. Dr. N Power Electronics. Go to this playlist, Dr. N Power Electronics, and look for that one, single phase, solving for an extinction angle from the half wave rectifier current equation. So this is using the half wave rectifier uncontrolled version, right? But it shows you how to use the calculator to find for beta. So you can apply that for the single phase full wave control rectifier as well, right? So okay, tomorrow 3 to 4.5 is 1.5 hours. I hope you the best, do not copy from others. Okay, it is, I mean, you try your best. Sometimes your friend also may not get a correct answer. It's better for you to if it's an open book, it is an open book, so please make sure that you can open the lecture note, the monograph. You can refer to the solutions I've shared you before, isn't it? So make sure that don't just copy whatever your friend is. They may not get the same answers, okay, or they may not be as correct as you. Okay, so all the best, inshallah. So the we see again next week, inshallah. So okay, for that, assalamualaikum warahmatullahi wabarakatuh.